Imagine this, you're on a spaceship, the engines roar to life, you accelerate, the stars outside your window begin to stretch into lines of light, your speedometer climbs, 10% the speed of light, then 50, then 90, and then at some impossible moment you hit it, the ultimate speed limit of the universe, the speed of light itself. What happens to time? Does it slow down? Does it crawl? Does it simply stop? And one quick question, if you could freeze time for just 1 hour, what would you do? Let me know in the comments below. I'll pin the most creative answer. Now let's begin. The year was 1905. Albert Einstein was 26 years old. He wasn't a professor at a prestigious university. He wasn't working at a famous laboratory. He was a third-class technical expert at a patent office in Bern, Switzerland. His job? Reviewing patent applications for electromagnetic devices. But in his spare time, on lunch breaks, during quiet evenings, in the margins of his notebooks, he was wrestling with a question that had haunted physicists for decades. A question about light, motion, and the very fabric of space and time. The problem went something like this. Imagine you're running alongside a beam of light. You run faster and faster, getting closer and closer to the light's speed. What would the light look like if you could somehow match its pace? Would it appear frozen like a still photograph? Would you see the electromagnetic wave suspended in mid-air, its peaks and valleys locked in place? Classical physics said yes, if you catch up to something, it should appear stationary relative to you. That's just common sense. That's how it works with cars on a highway, with runners on a track, with anything moving through space. But there was a problem, a deep, fundamental problem. James Clerk Maxwell's equations. The mathematical laws describing electricity, magnetism, and light. They said something else entirely. They said the speed of light was fixed, constant, unchanging. It didn't matter if you were standing still or hurtling through space at tremendous velocities. Light would always race away from you at exactly the same speed. This seemed absurd. It violated everything intuition told us about how motion works. Einstein spent years turning this paradox over in his mind. And then in the spring of 1905, the answer came to him, not through complex mathematics, not through elaborate experiments, but through a simple, breathtaking realization. What if everyone was right? What if the speed of light truly was constant for all observers? And what if, to make this possible, something else had to give? That something else was time. In June of 1905, Einstein submitted a paper to the journal Annalen der Physik. Its title, translated from German, was On the Electrodynamics of Moving Bodies. It contained no footnotes, no citations, no references to other scientists' work, just 30 pages of pure thought. The paper introduced what we now call special relativity, and it rested on two simple postulates, two assumptions that seemed almost too basic to be revolutionary. First, the laws of physics are the same for all observers moving at constant velocities. There is no special rest frame of the universe. If you're in a smoothly moving train with the windows covered, there's no experiment you can perform to prove you're moving rather than standing still. Second, the speed of light in a vacuum is the same for all observers, regardless of their motion or the motion of the light source. It doesn't matter if you're rushing toward a beam of light or running away from it. You will always measure it traveling at exactly 299,792,458 meters per second. These two postulates seem innocent enough, but when you follow them to their logical conclusions, reality starts to warp in ways that defy everyday experience. Here's what happens. If the speed of light is truly constant for everyone, then something else must change to accommodate this. And that something is the passage of time itself. Imagine two observers. One is standing still, the other is zooming past at high velocity. According to Einstein, these two observers will disagree about how much time passes between events. The moving observer's clock will tick more slowly compared to the stationary observer's clock. Not because the clock is broken, not because of some mechanical failure, but because time itself flows differently depending on your motion through space. This effect is called time dilation. And it's not a theory anymore. It's a measured, verified, undeniable fact of our universe. If you're enjoying this exploration, if these ideas are sparking something in you, make sure to subscribe to the channel and give this video a like. It helps this channel grow so I can bring you more content like this. Now, I know mathematics can feel intimidating, but stay with me here because this is where things get truly mind-bending. Einstein derived a formula to describe exactly how much time slows down for a moving object. It's called the Lorentz factor, named after the Dutch physicist Hendrik Lorentz, who first discovered it mathematically. Here's what it says. Take the number 1. Subtract from it the square of your velocity divided by the square of the speed of light. Then take the square root of that result. The Lorentz factor is 1 divided by that square root. I know that sounds complicated, so let me give you some examples. If you're moving at 10% the speed of light, roughly 108 million kilometers per hour, time slows down by about 0.5% for you. You'd barely notice. At 50% the speed of light, time slows down by about 15%. 1 hour for you would be roughly 1 hour and 10 minutes for someone standing still. At 90% the speed of light, time has slowed by more than half. 2 hours pass for you, while over 4.5 hours pass for a stationary observer. At 99% the speed of light, time crawls. For every hour you experience, 7 hours pass for someone at rest. At 99.9%, 1 hour for you equals over 22 hours for them. You see the pattern. As you approach the speed of light, time dilation increases dramatically. The effect compounds, it accelerates, it runs away toward infinity. And here's the critical point. When you plug the speed of light itself into the equation, when your velocity equals 299,792,458 meters per second exactly, something strange happens. The Lorentz factor becomes infinite. The math literally divides by 0. And that means, from the perspective of a photon traveling at light speed, time doesn't just slow down, it stops completely. An infinite amount of time passes for the rest of the universe, while 0 time passes for the photon. Let's pause here, because this is where our intuition completely breaks down. Think about a photon, a single particle of light, leaving a distant star. Let's say that star is Alpha Centauri, our nearest stellar neighbor, located about 4.3 light-years away. From our perspective on Earth, that photon takes 4 years and roughly 4 months to reach us. It crosses nearly 41 trillion kilometers of empty space. We could calculate its position at any point during that journey, but from the photon's perspective, from the reference frame of the light itself, nothing happens. No time passes, not a femtosecond, not a Planck time, not the smallest measurable interval. The photon's departure and its arrival are the same moment. The emission from the star and the absorption into your eye occur simultaneously for the photon. This is almost impossible to wrap your head around. How can a journey of 4 years take no time? How can something travel 40 trillion kilometers in an instant? The answer lies in understanding that time is not universal. Time is not a river flowing at the same rate everywhere in the cosmos. Time is personal. Time is relative. Your time depends on your motion through space. And for something moving at the speed of light, time simply doesn't exist. Here's where we need to be very careful. Very precise, because the physics community is extremely clear on this point. Nothing with mass can ever reach the speed of light. Not almost nothing, not practically nothing, absolutely nothing that has even a single atom of mass. Why? because of another consequence of Einstein's equations. As an object with mass accelerates, it gains energy. And as it gains energy, it gains mass, not rest mass, not the mass you'd measure on a bathroom scale, but relativistic mass. The effective mass that resists further acceleration. As you approach the speed of light, your relativistic mass increases without bound. It climbs toward infinity. And that means the energy required to accelerate you further also climbs toward infinity. To push anything with mass to exactly the speed of light would require an infinite amount of energy. And since the universe contains only a finite amount of energy, this is fundamentally impossible. This isn't a technological limitation. It's not that our rockets aren't powerful enough, it's not that we haven't discovered the right fuel, it's a built-in feature of space-time itself. The universe has a speed limit, and it enforces it absolutely. So when we ask, does time stop at the speed of light, we're really asking about entities that travel at light speed naturally, entities that have no mass, entities like photons. Photons are strange. They're not like anything you encounter in daily life. They have no mass, no charge, no size in the traditional sense. They're ripples in the electromagnetic field, packets of energy that somehow behave like both waves and particles depending on how you observe them. And they're born traveling at the speed of light. They don't accelerate, they don't speed up from rest. The moment a photon comes into existence, whether from the nuclear furnace of a star, the filament of a light bulb, or the screen you're watching right now, it's already moving at maximum velocity. It has no choice. Massless particles must travel at light speed. It's not optional, it's mandatory. This is one of the strangest features of our universe. Mass and speed are intimately connected. If you have mass, you can travel at any speed below light speed, but never at or above it. If you have no mass, you must travel at exactly light speed. Never slower, never faster. Exactly that speed always. And this brings us back to our central question. If photons travel at light speed and if time stops at light speed, then photons exist in a state of eternal timelessness. From their perspective, if we can even use that word. The entire history of the universe unfolds in a single instant. Consider this. A photon released during the cosmic microwave background radiation, the afterglow of the Big Bang. That photon has been traveling for about 13.8 billion years from our perspective. It has crossed almost the entire observable universe. It has witnessed galaxies forming, stars igniting and dying, planets coalescing from dust and debris. But for that photon, no time has elapsed. Not a moment. The Big Bang and the present day are simultaneous events. The birth of the cosmos and this very second exist in the same frozen instant. Does that mean the photon has experienced 13.8 billion years of cosmic history? Absolutely not. It hasn't experienced anything. Experience requires time. Experience requires change. Sequence. Before and after. And a photon has none of these. It exists outside of time altogether. This is where language starts to fail us. We're creatures of time. Every thought you have, every word I speak, every heartbeat in your chest, these all require duration. They require moments strung together like beads on a string. We literally cannot imagine what it means to exist without time, because imagination itself is a temporal process. And yet, the mathematics tells us this timeless state is real. The equations don't lie. They've been tested thousands of times in countless experiments, and they always hold true. Speaking of experiments, let's talk about proof. Because all of this would be mere philosophical speculation if we couldn't actually measure time dilation in the real world. The first direct confirmation came in 1971. Two physicists named Joseph Hafele and Richard Keating performed an elegantly simple experiment. They took 4 cesium atomic clocks, the most precise timekeeping devices then available, and loaded them onto commercial airplanes. 2 planes flew eastward around the world, 2 flew westward. Meanwhile, reference clocks remained stationary at the United States Naval Observatory. When the traveling clocks returned, they were compared to the stationary ones. And guess what? They disagreed. The clocks that had flown east, moving with Earth's rotation, had lost about 59 nanoseconds. The clocks that flew west, moving against Earth's rotation, had gained about 273 nanoseconds. These differences matched Einstein's predictions almost perfectly. Time had literally passed at different rates for the moving clocks versus the stationary ones. The effect was tiny, billionths of a second, but it was real, measurable, undeniable. And this was just the beginning. In 1976, NASA launched Gravity Probe A. It carried an extremely precise hydrogen maser clock to an altitude of 10,000 kilometers. The clock was compared to identical clocks on the ground using radio signals. Once again, time dilation was confirmed. The clock in space, moving at high velocity and experiencing weaker gravity, ticked at a different rate than clocks on Earth's surface. These weren't theoretical predictions anymore. They were experimental facts, written in the language of nanoseconds and atomic oscillations. But perhaps the most dramatic evidence comes from particle physics. Deep underground at facilities like CERN in Switzerland and Fermilab in Illinois, scientists accelerate subatomic particles to velocities incredibly close to light speed. And when they do, something remarkable happens. Consider the muon. It's a particle similar to an electron, but about 207 times heavier. Muons are unstable. When they're sitting still in a laboratory, they decay in about 2.2 microseconds on average. That's 2 millionths of a second. Blink and you've missed thousands of muon lifetimes. But when muons are created in the upper atmosphere by cosmic rays and come screaming toward Earth at 99.9% the speed of light, something strange occurs. They survive much longer than 2.2 microseconds. They travel distances that should be impossible given their brief lifespans. Why? Because time has slowed down for them. From our perspective, watching from the ground, the muon's internal clock is ticking much more slowly. What feels like 2.2 microseconds to the muon is actually many times longer in our reference frame. The muon isn't living longer in any absolute sense. It's experiencing less time. This has been measured countless times. The data is overwhelming. Fast-moving particles age more slowly than identical particles at rest. Time dilation is not speculation, it's experimental fact. In November 2025, physicists at the MAGIC telescopes in the Canary Islands published groundbreaking results. They analyzed very high-energy gamma rays from distant cosmic sources and confirmed the constancy of the speed of light with unprecedented precision. These gamma-ray photons had traveled across billions of light-years of space, and they arrived exactly when Einstein's equations predicted. No variation, no deviation. Special relativity passed yet another stress test. Even more recently, in January 2026, scientists announced that Einstein's speed of light rule had survived its toughest cosmic stress test yet. Researchers studied light from extremely distant astronomical objects and found zero evidence of any violation of special relativity. After more than a century, Einstein's framework remains unbroken. But wait, let's think carefully about what we're actually claiming here. When we say time stops for a photon, we're making a statement that borders on meaningless from a strict physics perspective. And I want to be honest with you about this because science demands honesty. Even when the honest answer is complicated, here's the issue. In special relativity, we talk about reference frames, perspectives from which you measure space and time. Your reference frame is wherever you are, moving however you're moving. My reference frame is wherever I am. We can compare our measurements and find they differ in predictable ways. But here's the catch. You cannot construct a valid reference frame for something traveling at the speed of light. Think about it. A reference frame requires a clock, something to measure time. But if time doesn't pass for a photon, there's no clock. There's no measurement. There's no perspective in any meaningful sense. So when physicists say time stops at the speed of light, they're really describing a limit. They're saying, as you get closer and closer to light speed, time slows down more and more in the limit at exactly light speed. The formula says time dilation becomes infinite. But you can never actually reach that limit if you have mass. And if you don't have mass, the concept of your experience of time doesn't apply. It's like asking, what's north of the North Pole? The question uses familiar words, but it doesn't actually point to anything real. There is no valid answer because the question itself breaks down at that extreme. This is one of those moments where physics bumps against the limits of human language. Our words evolve to describe the everyday world. A world of moderate speeds, familiar distances, human timescales. When we venture into the realm of light speed and relativistic effects, our vocabulary strains and sometimes snaps. Does time stop at the speed of light? Mathematically, yes. The equations point that way. Experientially, the question may not even make sense. But here's what we can say with certainty. For anything approaching the speed of light, time profoundly slows down. And this has real consequences. Consequences that matter for space travel, for GPS satellites, for particle accelerators, for our understanding of the cosmos. Let me give you an example that brings this home. Imagine you board a spacecraft capable of accelerating to 99.999% the speed of light. You set course for the Andromeda Galaxy, our nearest major galactic neighbor, located about 2.5 million light-years away. From Earth's perspective, your journey takes a little over 2.5 million years. Civilizations rise and fall while you're in transit. Ice ages come and go. The continents drift across the planet's face. Entire species evolve and go extinct. But from your perspective? Thanks to time dilation, the trip takes only about 35 years of your personal time. You age 35 years. You experience 35 years of meals, sleep cycles, thoughts, heartbeats. And then you arrive at Andromeda. You haven't traveled faster than light. That's still impossible, but you've taken a shortcut through time itself. You've let the universe's peculiar geometry carry you across millions of light years while barely aging. This is real. This is physics. This is what Einstein's equations tell us. And it leads to one of the most mind-bending implications of special relativity, the twins paradox. Imagine two twins. One stays on Earth. The other boards our hypothetical spacecraft and makes a round trip to a nearby star at near light speed. When the traveling twin returns, she finds her sibling has aged dramatically, decades perhaps, while she herself has aged only a few years. They're no longer the same age. Time has literally passed differently for them. This isn't an illusion or a trick of perception. It's the actual physical passage of time diverging for two people based on their motion through space. This seems paradoxical. Surely if motion is relative, each twin should see the other's clock running slow. Shouldn't the effect be symmetrical? The resolution lies in the fact that the traveling twin accelerates and decelerates. She changes direction. She doesn't remain in a single inertial reference frame throughout her journey. And that asymmetry breaks the apparent paradox. The twin who stays home remains in one reference frame. The twin who travels switches between multiple reference frames. When you account for this properly, the mathematics works out perfectly, and the traveling twin really does age less. This has been confirmed experimentally with atomic clocks on aircraft and satellites, it's not speculation, it's measured reality. So what does all this mean for you, for your place in the cosmos, for the nature of existence itself? We'll explore that next. Let's zoom out for a moment. Let's step back from the equations and the experiments and consider what all of this reveals about the nature of reality, because the implications of time dilation extend far beyond physics laboratories and thought experiments. They touch on the deepest questions humans have ever asked. What is time? Is it fundamental to the universe, or is it something that emerges from deeper structures? And perhaps most unsettling of all, is the present moment, this instant you're experiencing right now. Is it truly special, or is it just one slice of a larger reality where past, present, and future all exist simultaneously? Einstein himself wrestled with these questions, and he came to a startling conclusion, one that disturbed even him. In the framework of special relativity, there is no universal now. Think about what that means. When you look up at the night sky, you're not seeing the universe as it is. You're seeing it as it was. The light from the moon left its surface about 1.3 seconds ago. The light from the sun departed 8 minutes and 20 seconds before it reached your eyes. The light from Alpha Centauri has been traveling for over 4 years, and the light from the Andromeda Galaxy, that began its journey 2.5 million years ago, before humans even existed. But here's where it gets truly strange. According to special relativity, the question of what is happening right now on Andromeda doesn't have a definitive answer. It depends on how you're moving. If you're standing still relative to Andromeda, you might say that right now some alien civilization is going about its daily business. But if you start walking toward Andromeda, just walking at a leisurely pace, your slice of now tilts. Suddenly, the events you consider simultaneous on Andromeda shift by thousands of years. Walk the other direction, and they shift again in the opposite temporal direction. This is called the relativity of simultaneity, and it suggests something profound. Events that are in your future might already be in someone else's past, and events in your past might still be in someone else's future. The universe doesn't have a single, objective now that everyone agrees on. Your now is different from my now. And both are different from the now of an alien traveling at high speed through a distant galaxy. What does this mean? Some physicists and philosophers have argued that it points to a block universe, a four-dimensional structure where time is just another dimension, like length, width, and height. In this view, the past isn't gone, and the future isn't yet to come. They both exist eternally, the entire history of the cosmos, from the Big Bang to the heat death of the universe, is laid out like a vast frozen sculpture. And our experience of time flowing, of the present moment moving forward, is just an illusion, a feature of how conscious minds process information. This is a deeply controversial idea. Many physicists reject it. They argue that the block universe interpretation reads too much into the mathematics, that just because relativity lacks a universal now doesn't mean the future already exists, but the debate continues. And it highlights how questions about time and light speed connect to the most fundamental mysteries of existence. Let's bring this back to something more tangible, more immediate. Let's talk about how time dilation affects technology you use every single day. Pull out your smartphone. If it has GPS, which it almost certainly does, you're holding a device that would be completely useless without accounting for relativistic effects. The global positioning system relies on a constellation of about 31 satellites orbiting Earth at an altitude of roughly 20,000 kilometers. Each satellite carries an extremely precise atomic clock. Your phone receives signals from multiple satellites and calculates your position based on the tiny differences in arrival times of those signals. Speed matters here. Light travels fast, but distances matter too. A difference of just a few nanoseconds in timing translates to an error of about a meter in position. Here's the problem. Those satellites are moving at about 14,000 kilometers per hour relative to the ground. That's fast enough for special relativistic time dilation to kick in. The satellite clocks tick slightly slower than clocks on Earth, by about 7 microseconds per day. At the same time, the satellites are higher up in Earth's gravitational field. And this is where general relativity comes in, Einstein's other great theory. Clocks in weaker gravitational fields tick faster. This effect adds about 45 microseconds per day. The two effects work in opposite directions, but they don't cancel out. The gravitational effect wins. Overall, GPS satellite clocks gain about 38 microseconds per day relative to ground clocks. That might sound tiny, but remember, light travels about 11 kilometers in 38 microseconds. Without relativistic corrections, GPS errors would accumulate at a rate of roughly 10 kilometers per day. Within a week, your navigation app would be placing you in the wrong city. Within a month, possibly the wrong country. So every GPS satellite has its clocks deliberately set to tick at a slightly different rate before launch. The engineers pre-compensate for relativistic effects. Your ability to navigate to a new restaurant or find your way home, that everyday miracle. Depends on Einstein's insights about time and motion. Relativity isn't just abstract theory, it's built into the infrastructure of modern civilization. But GPS is just the beginning. Time dilation matters for particle accelerators like the Large Hadron Collider at CERN. It matters for synchronizing telecommunications networks. It matters for the precise timing required in financial trading systems. Every time data moves at the speed of light through fiber optic cables, relativistic effects are at play. We've built a world that depends on the physics Einstein uncovered over a century ago. And most people have no idea. Let's push further. Let's think about what happens at even more extreme velocities. We've talked about what it would be like to travel at 99% the speed of light, or 99.9%. But what about 99.999999%? As you add more nines, something interesting happens. Time dilation becomes so extreme that you could traverse the entire observable universe within a single human lifetime. Think about that. The observable universe is about 93 billion light-years in diameter. Light itself takes 93 billion years to cross it. But if you could accelerate continuously at a comfortable 1g, the same acceleration you feel from Earth's gravity, you would experience something miraculous. From your perspective inside the ship, you could reach the edge of the observable universe in about 45 years. You'd age 45 years. But the universe outside would have aged billions upon billions of years. Everyone you ever knew would be long dead. Earth itself would be unrecognizable. The sun might have already swelled into a red giant and consumed our planet. This is the true cost of relativistic travel. You can cross the cosmos in a human lifetime, but you can never come home, not to the world you left behind. Your journey is one way in more than just space. It's one way in time. The faster you travel, the more you become unmoored from the temporal flow that everyone else experiences. Science fiction often explores this theme. The lonely astronaut returning to find centuries have passed, loved ones turned to dust, civilizations risen and fallen. It's a powerful emotional hook, but it's not just fiction, it's physics. If we ever develop the technology to travel at relativistic speeds, this is the reality that awaits us. Some physicists have speculated about ways around this limitation. Wormholes, Alcubierre warp drives, shortcuts through space-time that might allow faster-than-light travel without violating Einstein's equations. These remain highly theoretical. Most require exotic matter with negative energy density. Stuff that may not exist outside of mathematical abstractions, but they're not strictly impossible according to current physics. The universe might contain loopholes we haven't discovered yet. For now, though, we're bound by light speed, bound by the strange rules Einstein laid down, bound by a cosmos where time is elastic, personal, mutable, where your clock and my clock can disagree about how much time has passed. And both of us can be right. Let's return to photons for a moment. Because there's another aspect of their timeless existence that we haven't explored. It concerns something called proper time. In relativity, proper time is the time measured by a clock traveling with an object. It's the object's personal experience of duration. For you sitting wherever you are right now, proper time ticks away steadily, second by second, heartbeat by heartbeat. For a fast-moving muon, proper time ticks more slowly relative to our clocks, but it still ticks. The muon still experiences duration, just less of it. For a photon, proper time is zero, exactly zero, always. The photon's personal clock never ticks, not once, not ever. In the most literal mathematical sense, photons do not experience the passage of time. They exist in an eternal present, if present is even the right word. This leads to a strange philosophical puzzle. Does the photon exist? We certainly detect photons. We measure their energy. We use them to see, to communicate, to understand the universe. But existence, in the way we normally understand it, requires persistence through time. A rock exists because it's here now, and it was here a moment ago, and it will be here a moment from now. Its existence has duration. A photon has no duration. From its own perspective, if perspectives are even meaningful, its creation and its destruction are the same event. It doesn't persist. It simply is, at one timeless, eternal instant. This is deeply weird. And physicists don't fully agree on how to interpret it. Some argue we shouldn't take the photon's perspective seriously because, as I mentioned earlier, you can't actually construct a valid reference frame for a photon. Others argue that the mathematics is telling us something profound about the nature of light, and perhaps about the nature of time itself. Here's one way to think about it. Time, as we experience it, might be a consequence of having mass. Massive particles move through space-time in a particular way. They experience duration, they have histories, they accumulate memories if they're complex enough to have memories. But massless particles like photons take a different path through space-time. A path where temporal duration shrinks to zero. In a sense, photons aren't traveling through time at all. They're taking a shortcut. A null path. A trajectory where space and time conspire to produce zero proper time. This brings us to one of the deepest questions in physics. What is time, really? We've been talking about time slowing down, time stopping, time passing at different rates for different observers. But what is this thing that can be stretched and compressed like taffy? Is time a fundamental feature of reality, or is it something that emerges from deeper structures? Something that appears real to us but is actually an illusion? Physicists have been arguing about this for centuries, and they still don't agree. Newton thought time was absolute, a cosmic metronome ticking away in the background of the universe, the same everywhere, the same for everyone, independent of matter and motion, just a stage on which the drama of physics plays out. Einstein shattered that view. He showed that time is relative, entangled with space, dependent on motion and gravity. Not a fixed background, but a dynamic player in the physics itself. Space-time curves, warps, bends. And time flows differently depending on where you are and how fast you're moving. But even Einstein's view might not be the final word. Some physicists working on quantum gravity, the effort to unify Einstein's general relativity with quantum mechanics, suggests that time might not be fundamental at all. It might emerge from something deeper, something we don't yet understand. In some approaches, like loop quantum gravity, space-time itself is made of discrete chunks, tiny granules of space and time woven together in a quantum fabric. Time doesn't flow smoothly. It ticks, in unimaginably small increments, about 10 to the minus 43 seconds per tick. The Planck time, the smallest meaningful interval of duration. Other approaches go even further. In the Wheeler-DeWitt equation, a central equation in one approach to quantum gravity, time doesn't appear at all. The equation describes the quantum state of the entire universe. And it's timeless. Completely static, no past, no future, just an eternal mathematical structure. How do we reconcile this with our experience of time flowing, of one moment following another? This is called the problem of time in quantum gravity, and it remains unsolved. Some physicists, like Julian Barber, argue that time truly is an illusion, that what we call the flow of time is just how our brains process a static, timeless reality. Each moment exists independently, like frames of a film strip. Our consciousness strings them together and creates the illusion of motion, of flow, of before and after. But the film strip itself just is, all at once, eternally. This is deeply counterintuitive. Every fiber of your being screams that time is real, that the present moment is special, that the past is gone and the future is yet to come. But intuition has led us astray before. Intuition told us the Earth was flat, that the sun revolved around us, that space and time were absolute. Science has repeatedly shown that reality is stranger than our monkey brains evolved to comprehend. Let's shift gears and talk about something more concrete, something that connects time dilation to the future of humanity. Let's talk about interstellar travel. If we ever want to become a truly spacefaring civilization, if we want to reach other stars, other planets, perhaps other life, we will have to grapple with the realities of relativistic travel. The distances involved are staggering. The nearest star system, Alpha Centauri, is about 4.3 light-years away. That means light, the fastest thing in the universe, takes over 4 years to make the journey. With our current technology, it would take tens of thousands of years. But what if we could build faster ships, not faster than light? That remains impossible, but a significant fraction of light speed, let's say 10%. At that speed, we could reach Alpha Centauri in about 43 years, a human lifetime. Barely, but doable. The travelers would age 43 years. The people on Earth would also age about 43 years. Time dilation at 10% light speed is minimal, only about 0.5%, hardly noticeable. Now let's push to 50% light speed. The journey shrinks to about 8.6 years of ship time. But here's where it gets interesting. Due to time dilation, the travelers age only about 7.4 years, while people on Earth age the full 8.6 years. The difference is small, but it's there, real, measurable. Now let's go extreme. 99% light speed. The journey from Earth's perspective takes about 4.34 years, but the travelers, they experience only about 7 months. 7 months of ship time to cross over 4 light years. They step off the ship having aged half a year, while nearly 4.5 years have passed on Earth. At 99.9% light speed, the asymmetry becomes even more dramatic. The travelers experience only about 10 weeks. 10 weeks to reach another star system. Meanwhile, over 4 years pass on Earth. The faster you go, the more time becomes your ally. The more you can compress decades and centuries into months and years of personal experience. This is the promise of relativistic travel. You can reach the stars within a human lifetime. You can cross the galaxy if you're willing to let millions of years pass for everyone else. The universe becomes accessible, in theory. In practice, the engineering challenges are almost insurmountable. Accelerating a spacecraft to 99% light speed requires enormous amounts of energy. Protecting the crew from interstellar dust and radiation at those speeds is nearly impossible with current technology. And then there's the problem of slowing down when you arrive. You can't just hit the brakes. You need to carry enough fuel to decelerate, which means more mass, which means more energy to accelerate in the first place. It's a brutal equation, but physicists and engineers are working on it. Concepts like laser propulsion, antimatter engines, nuclear pulse drives. These are being studied seriously. The Breakthrough Starshot initiative aims to send tiny probes to Alpha Centauri at 20% light speed using powerful ground-based lasers. The probes would be small, only a few grams, no humans aboard, but they could reach the nearest star in about 20 years and beam back images. Data? Proof that interstellar travel is possible. For crewed missions, we'll need something bigger, something bolder, but the physics allows it. Einstein's equations don't forbid us from reaching the stars, they just make it very, very hard, and they guarantee that any interstellar travelers will be forever separated from the world they left behind. Not just by distance, but by time itself. Let's consider another implication of time dilation, one that's rarely discussed. It concerns the nature of causality, cause and effect, the fundamental relationship that underlies all of physics, all of logic, all of our understanding of the world. We take for granted that causes precede effects, that if event A causes event B, then A happens before B. Always, for everyone. But special relativity complicates this picture. Remember the relativity of simultaneity I mentioned earlier? Events that are simultaneous for one observer might not be simultaneous for another. The order of events can depend on your motion. This sounds like it could lead to paradoxes. If event A happens before event B for me, but event B happens before event A for you, doesn't that scramble cause and effect? Could effects precede their causes from some perspectives? The answer is no, but the reason is subtle and beautiful. Special relativity preserves causality through a distinction between time-like and space-like separations. If two events are causally connected, if one could have influenced the other, then their order is the same for all observers. Everyone agrees that the cause came first, but if two events are too far apart in space and too close together in time for any signal, even light, to travel between them, then they're space-like separated, and different observers can disagree about their order. This is where the speed of light becomes not just a speed limit, but a guardian of causality. Nothing can travel faster than light, and this ensures that causes always precede effects for any causally connected events. If faster than light travel were possible, you could send signals into the past. You could create paradoxes. You could kill your grandfather before you were born. The universe prevents this, not through some physical barrier, but through the structure of space-time itself. Causality is built into the geometry of reality. This is part of why physicists are so confident that nothing can exceed light speed. It's not just about energy requirements or engineering challenges, it's about the logical structure of the universe. Faster than light travel would break causality. And a universe without causality would be chaos. Effect without cause. Future influencing past. An incomprehensible tangle of paradoxes. Whatever the universe is, it's not that. So the speed limit holds, and time, strange as it may be, continues to make sense. We've covered a lot of ground, from Einstein's thought experiments to atomic clocks on airplanes, from muons in particle accelerators to GPS satellites in orbit, from the block universe to the possibility of interstellar travel. But let's bring this back to the core question we started with. Does time stop at the speed of light? Here's my honest answer. As honest as I can be, given what physics tells us. For objects approaching the speed of light, time slows down dramatically. This is not speculation, it's measured fact. The closer you get to light speed, the more time dilates. In the limit, at exactly the speed of light. The equations say time stops completely. But, and this is crucial, nothing with mass can ever reach that limit. The speed of light is asymptotic. You can get arbitrarily close, but never arrive. For massless particles like photons, the situation is even stranger. They travel at exactly light speed, and the equations suggest their proper time is zero. They experience no duration, but we can't actually construct a valid reference frame for a photon, so asking what time is like for a photon may not be a meaningful question. The most accurate thing we can say is this: time and speed are intimately related. The faster you move through space, the slower you move through time. And at the speed of light, this relationship reaches its extreme. Motion through space is maximized, motion through time is minimized, reduced mathematically to zero. Whether this means time stops in any experiential sense is a question that physics alone may not be able to answer. It touches on consciousness, on the nature of experience, what it means to exist at all. What I find most remarkable about all of this is how it reveals the hidden structure of reality. Time feels so solid, so fundamental, so obvious. But scratch the surface and you find something fluid, relative, dependent on motion and gravity, entangled with space in ways our ancestors could never have imagined. The universe is stranger than we thought, stranger perhaps than we can think, and yet we can understand it, at least partially, through mathematics, through experiments, through careful reasoning. A species of evolved apes on a small rocky planet has figured out that time is relative, that nothing can exceed light speed, that the geometry of space-time itself preserves causality. We've built technologies that depend on this knowledge. We've confirmed it to extraordinary precision. We've peered into the heart of reality and glimpsed something beautiful. Let's dive deeper into something we touched on earlier, something that deserves its own exploration, the nature of light itself, because to truly understand why time stops at light speed, we need to understand what light actually is. And trust me, the answer is stranger than you might expect. For most of human history, we had no idea what light was. The ancient Greeks debated it endlessly. Some thought light was a stream of particles emitted by our eyes, reaching out to touch objects and bring back information. Others thought light came from objects themselves, traveling to our eyes as some kind of invisible messenger. The debate raged for centuries, and neither side had the tools to settle it. Then came the scientific revolution, and with it, new ways of probing nature's secrets. In the 1600s, Isaac Newton conducted his famous experiments with prisms. He showed that white light is actually a mixture of colors, a spectrum ranging from red to violet. He believed light was made of tiny particles, corpuscles he called them, little bullets of illumination shooting through space. But around the same time, a Dutch scientist named Christian Huygens proposed something different. He thought light was a wave, like ripples on a pond or sound waves traveling through air. The debate between particles and waves would continue for another 2 centuries, and in the end, both sides would turn out to be right in a way that defies common sense. In the early 1800s, a British scientist named Thomas Young performed a crucial experiment, the double-slit experiment. He shone light through 2 narrow slits and observed the pattern it made on a screen behind them. If light were made of particles, you'd expect 2 bright bands, one behind each slit, but that's not what Young saw. Instead, he observed a pattern of alternating bright and dark bands, an interference pattern, the kind of pattern you only get with waves. When crests meet crests, you get brightness. When crests meet troughs, you get darkness. Light was definitely a wave. Case closed, or so it seemed. The wave theory of light triumphed for decades. James Clerk. Maxwell unified electricity, magnetism, and light into a single elegant theory. Light was an electromagnetic wave, oscillating electric and magnetic fields propagating through space. The equations were beautiful, the predictions were accurate, everything made sense. Then came the year 1900, and everything fell apart. A German physicist named Max Planck was studying something called blackbody radiation, the glow emitted by hot objects. The existing theories predicted something absurd, that hot objects should emit infinite amounts of ultraviolet light. This was called the ultraviolet catastrophe, and it clearly didn't match reality. Hot objects don't blind us with infinite ultraviolet radiation. Something was wrong with the physics. Planck found a solution, but it required a radical assumption. He proposed that light energy comes in discrete packets, quanta, not continuous waves, but little bundles of energy, each with an energy proportional to its frequency. He didn't fully believe his own idea. He called it a mathematical trick, a desperate measure to make the equations work. But it worked. The ultraviolet catastrophe was solved. 5 years later, Einstein took Planck's idea seriously, very seriously. In another of his miraculous 1905 papers, Einstein proposed that light actually is made of particles, quanta of electromagnetic energy. We now call them photons. He used this idea to explain the photoelectric effect, the way light can knock electrons out of metals. The wave theory couldn't explain it, but photons could. So which is it? Is light a wave or a particle? The answer, brace yourself, is both and neither. Light is something that has no analog in everyday experience, something that behaves like a wave in some experiments and like a particle in others. This is called wave-particle duality. And it's one of the central mysteries of quantum mechanics. When light travels through space, it behaves like a wave. It diffracts around obstacles. It interferes with itself. It spreads out and bends. But when light interacts with matter, when it's absorbed or emitted, it behaves like a particle, a discrete packet of energy, a photon. The double-slit experiment shows both behaviors at once. Even single photons sent one at a time through the slits eventually build up an interference pattern, as if each photon goes through both slits simultaneously, interfering with itself before landing as a single point on the detector. This is not a metaphor, this is not a simplification for popular audiences. This is what the experiments actually show. Light does not fit into our categories, it transcends them. It exists in a realm where wave and particle are just approximations, useful in some contexts, misleading in others. Reality itself is stranger than our concepts. And here's where it connects to time dilation. Photons, these strange wave-particle hybrids, travel at exactly the speed of light, always. In every reference frame, they have no mass. And because they have no mass, they must travel at light speed. They have no choice. From the moment of their creation to the moment of their destruction, they're moving at the cosmic speed limit. And as we've discussed, this means they experience no time. Their proper time is zero. Their journey through space, however vast, takes no duration from their perspective. They exist in a timeless state that we can barely comprehend. Wave-particle duality is strange enough, but combine it with the timelessness of light-speed travel, and you get something truly alien. Something that challenges every intuition we have about reality. And let's push this further. Let's talk about something even stranger, quantum entanglement, and its relationship to the speed of light. In 1935, Einstein and two colleagues published a paper pointing out something disturbing about quantum mechanics. They described a phenomenon we now call entanglement. Two particles can become connected in such a way that measuring one instantly affects the other, no matter how far apart they are. Measure the spin of one electron and you instantly know the spin of its entangled partner, even if that partner is on the other side of the galaxy. Einstein hated this. He called it spooky action at a distance. It seemed to violate the principle that nothing can travel faster than light. If measuring one particle instantly affects another light years away, isn't that faster than light communication? The answer, surprisingly, is no. And the reason is subtle and fascinating. Entanglement is real. It's been confirmed in countless experiments. The correlations between entangled particles are genuine. But you can't use entanglement to send information faster than light. Here's why. When you measure an entangled particle, you get a random result, spin up or spin down, with 50-50 probability. You can't control which result you get. And your partner, measuring the other particle, also gets a random result. It's only when you compare your results later, through a normal, slower-than-light communication channel, that you discover the correlations, that your random results were actually perfectly matched, or perfectly opposite. Depending on how the experiment was set up, the spookiness is real. The correlation is instantaneous, but no usable information travels faster than light. Causality is preserved. Einstein's speed limit holds. Even quantum mechanics, for all its strangeness, respects the cosmic speed limit. The universe is very careful about this, almost suspiciously careful. As if the speed of light isn't just a physical constant, but a fundamental principle, a law that cannot be broken, no matter how clever you are. This brings us to a question that physicists have pondered for decades. Why is the speed of light what it is? Why 299,792,458 meters per second? Why not faster? Why not slower? Why not infinite? The honest answer is, we don't know. The speed of light is one of the fundamental constants of nature, like the gravitational constant or Planck's constant. These numbers define the universe. They determine the strength of forces, the sizes of atoms, the rates of reactions, the structure of matter. Change them even slightly, and you get a very different cosmos, perhaps one where life is impossible. Some physicists speculate that these constants are not truly fundamental, that they emerge from deeper principles we haven't discovered yet. Others suggest that the constants vary across a multiverse, that our universe is just one of infinitely many, each with different values for these numbers. We happen to live in one where the constants allow for complexity, for chemistry, for life, for minds that can ask these questions. This is called the anthropic principle. And it's controversial. Some see it as profound, others as a cop-out, a way of avoiding the hard work of finding deeper explanations. The debate continues, and the speed of light remains mysterious. A cosmic speed limit with no clear origin, no obvious reason for being exactly what it is. But whatever its origin, the speed of light shapes everything. It determines how fast information can travel, how quickly causes can produce effects, how much time dilates at high velocities. It draws a boundary around what's possible and guards that boundary absolutely. Let's talk about something practical again, something that connects these abstract ideas to technology you might use in your lifetime. Let's talk about the future of computing and the strange role that light plays in it. Traditional computers use electrons, tiny charged particles flowing through silicon circuits. Electrons have mass. They travel much slower than light. They bump into atoms and generate heat. They're useful, but they have limits. As circuits get smaller, quantum effects start to interfere. We're approaching the end of Moore's law, the decades-long trend of computers getting faster and faster. The old tricks are running out. One alternative is optical computing, using light instead of electrons. Photons have no mass. They don't generate heat the way electrons do. They can carry information at the speed of light. Literally. Optical fibers already carry internet traffic around the world. Pulses of light encoding data, racing through glass at about 2/3 the speed of light, which is still incredibly fast, about 200,000 kilometers per second. But optical computing goes further. It uses light for processing, not just transmission. Photons interacting with each other, or with special materials, to perform calculations. The technology is still developing, but it holds promise. Faster processing, lower heat, new possibilities, and then there's quantum computing, which exploits the wave-particle duality of matter at the smallest scales. Quantum computers use qubits instead of classical bits. Qubits can exist in superposition, both 0 and 1 at the same time. They can be entangled with each other, creating correlations that classical computers can't match. For certain problems, quantum computers promise exponential speed-ups. Calculations that would take classical computers billions of years might take quantum computers mere seconds. Light plays a role here too. Photonic quantum computers use photons as qubits, their quantum states encoding information, their entanglement creating computational power, the speed of light, the timelessness of photons, the strange duality of light. All of these become tools for building the computers of the future. We're entering an era where the deep physics we've been discussing isn't just abstract theory, it's becoming engineering, practical technology, tools that will reshape civilization. The people who understand these principles will build the future, and everyone else will live in it. Let's take a step back and explore something we haven't fully addressed yet, the relationship between time and gravity, because Einstein didn't stop with special relativity. He spent the next 10 years developing something even more profound, a theory that would reveal time to be stranger than anyone imagined: general relativity. Special relativity tells us that time slows down when you move fast, but general relativity tells us something equally remarkable: time slows down in strong gravitational fields. The closer you are to a massive object, the slower your clock ticks. This isn't because gravity somehow interferes with your clock's mechanism. It's because gravity warps the fabric of space-time itself. And time is part of that fabric. Einstein arrived at this insight through another of his famous thought experiments. Imagine you're in an elevator. The cable snaps, you're in free fall, plummeting toward the ground. But inside the elevator, you feel weightless, you float. Objects released from your hand hover in mid-air. For a brief, terrifying moment, you can't tell the difference between falling in a gravitational field and floating in empty space with no gravity at all. This is the equivalence principle. Gravity and acceleration are locally indistinguishable. If you're in a rocket accelerating at 1g, you feel exactly the same as if you were standing on Earth's surface. Your weight feels identical. Dropped objects fall the same way. There's no experiment you can perform inside a sealed room to tell the difference. Einstein realized that this equivalence had profound implications. If acceleration affects time, and it does, we've measured it, then gravity must affect time too. Clocks in stronger gravitational fields tick more slowly than clocks in weaker fields. This is called gravitational time dilation, and it's just as real as the velocity-based time dilation we discussed earlier. The mathematics of general relativity describes gravity not as a force but as curvature of space-time. Massive objects like stars and planets bend the fabric of space and time around them. And this curvature affects everything, including light, including time. Near a massive object, time literally runs slower. Not because clocks are malfunctioning, but because time itself is stretched. This has been measured with extraordinary precision. In the 1970s, physicists placed atomic clocks at different altitudes and compared their rates. Clocks at higher altitudes, where gravity is slightly weaker, ticked faster than clocks at sea level. The difference was tiny, about 1 second every 30 million years. But it was there. Real. Measurable. GPS satellites, which we discussed earlier, experience both effects simultaneously. They're moving fast, which slows their clocks due to special relativity, but they're also higher up in Earth's gravitational field, which speeds their clocks due to general relativity. The gravitational effect is larger, so overall, the satellite clocks run faster than ground clocks. Engineers compensate for both effects to keep GPS accurate. But let's push this further. What happens in really strong gravitational fields near objects far more massive and compact than Earth? This is where things get truly extreme. This is where we encounter black holes. A black hole is what happens when matter gets compressed so densely that its gravitational field becomes overwhelming, inescapable. The escape velocity exceeds the speed of light, and since nothing can travel faster than light, nothing can escape. Not matter, not light, not information, nothing. The boundary of a black hole is called the event horizon. It's not a physical surface, it's a mathematical boundary, a point of no return. Cross it, and you're falling inward forever, or at least until you reach the singularity at the center, where density becomes infinite and the laws of physics as we know them break down. But here's what's truly mind-bending. Near a black hole's event horizon, gravitational time dilation becomes extreme. If you watch someone falling toward a black hole from a safe distance, you would see something strange. As they approach the event horizon, they appear to slow down. Their movements become sluggish, their clock ticks ever more slowly, their light becomes redder and dimmer as it fights to escape the gravitational well. And right at the event horizon, from your perspective, they appear to freeze. Time stops for them. They hover there, motionless, forever. Slowly fading from view as the last of their light struggles outward. But from their perspective, things are very different. They don't notice anything special as they cross the event horizon. They're in free fall, weightless. The stars above them might look strange, distorted by the curved space-time, but they don't feel a sudden stop. They don't experience time freezing. They just keep falling inward toward the singularity, where tidal forces eventually tear them apart, atom by atom. A process with the rather gruesome name of spaghettification. This disconnect between perspectives is one of the strangest features of black holes. Two observers can have completely incompatible experiences. From outside, the infalling observer never crosses the horizon. From inside, they cross it without noticing and plunge toward the center. Both perspectives are valid. Neither is wrong. They're just different slices of a reality that our intuitions cannot fully grasp. And at the singularity, at the center of the black hole, what happens there? The honest answer is that we don't know. General relativity predicts that density becomes infinite, that space-time curvature becomes infinite, that the equations themselves blow up and cease to make sense. This is a sign that general relativity is incomplete, that we need a theory of quantum gravity to understand what really happens at the heart of a black hole. Some physicists speculate that singularities don't really exist, that quantum effects prevent matter from collapsing to infinite density. Perhaps the center of a black hole is a region of incredibly compressed matter, or a gateway to another universe, or something we can't yet imagine. We simply don't know. Black holes remain one of the deepest mysteries in physics, but what we do know is that time behaves strangely near them. Gravitational time dilation reaches its extreme, and the interplay between space and time becomes impossible to ignore. Near a black hole, time and space are not separate things. They're woven together, twisted by gravity, transformed into something our everyday experience cannot prepare us for. In 2019, the Event Horizon Telescope collaboration released something remarkable: the first actual image of a black hole. Not an artist's impression, not a simulation, an actual photograph. It showed the supermassive black hole at the center of the galaxy Messier 87, about 55 million light-years from Earth. The image revealed a bright ring of hot gas surrounding a dark central shadow, the shadow of the event horizon itself, the boundary where light cannot escape. This was a triumph of human ingenuity. The image was constructed by linking radio telescopes around the world into a single virtual telescope the size of Earth. The data processing required years of effort by hundreds of scientists, and the result confirmed Einstein's predictions with stunning accuracy. General relativity passed another test. A century after Einstein first wrote down his equations, they still perfectly describe how gravity warps space-time. In May 2022, the same collaboration released an image of the black hole at the center of our own galaxy, Sagittarius A star, only about 27,000 light-years away. Much closer than Messier 87, but also much smaller and more variable, harder to image. Yet they did it, and again, Einstein was right. These images are more than just pretty pictures. They're windows into the extreme physics of space-time. They're laboratories for testing theories. They're proof that the universe is as strange as the mathematics predicts. Time really does slow down near massive objects. Space really does curve. Black holes really exist. And they really have event horizons where time, from an outside perspective, appears to stop. Let's connect this back to our central theme. We've been asking whether time stops at the speed of light, and the answer is yes, mathematically, at the limit of special relativity. But general relativity adds another dimension to this question. Time also slows down in gravitational fields, and at an event horizon, gravitational time dilation becomes infinite. Just like velocity-based time dilation at light speed, this is not a coincidence. At a deep level, special and general relativity are connected. They're both aspects of the same underlying geometry of space-time. The speed of light is woven into this geometry. It's the conversion factor between space and time, the number that relates meters to seconds, the cosmic constant that defines the structure of reality. When you move at light speed, your world line through space-time becomes what physicists call null. You're moving through space as fast as possible, and through time, not at all. When you're at an event horizon, something similar happens. The extreme curvature of space-time tilts your available paths so much that moving forward in time becomes equivalent to moving inward in space. The singularity isn't just ahead of you in space, it's ahead of you in time. Your future contains the singularity no matter which direction you try to move. Escape becomes impossible because the singularity is in your future, and you can't escape your own future. This is deeply strange, but it's what the mathematics tells us. And the mathematics has never been wrong. Every test, every observation, every experiment confirms that Einstein's framework is correct. Space and time are unified. Gravity is curvature. The speed of light is fundamental. And time dilation, whether from velocity or gravity, is real. Let's shift to something else, something that pushes at the boundaries of known physics. Let's talk about what happens when we try to combine relativity with quantum mechanics. Because here, at the frontier of knowledge, things get truly weird. Quantum mechanics describes the behavior of matter at the smallest scales, atoms, electrons, photons, quarks. It's incredibly successful. It explains chemistry, electronics, lasers, superconductors. Almost all of modern technology depends on quantum mechanics, but quantum mechanics and general relativity don't get along. They're like two brilliant theories that speak different languages. Each works spectacularly in its own domain. But when you try to combine them, the mathematics breaks down. General relativity describes gravity as the curvature of a smooth, continuous space-time. Quantum mechanics describes everything else as discrete, quantized, probabilistic. When you try to apply quantum principles to gravity, you get infinities. Nonsensical answers. Calculations that blow up and refuse to converge. This is the problem of quantum gravity, and solving it is one of the great challenges of modern physics. Several approaches exist. String theory suggests that the fundamental constituents of reality are not point particles, but tiny vibrating strings of energy. The different vibration modes of these strings correspond to different particles, and one of those modes naturally describes gravity. String theory is mathematically beautiful, but it requires extra dimensions of space. 6 or 7 of them, depending on the version, curled up so small we can't detect them, and it has made few testable predictions. After decades of work, string theory remains more a framework than a finished theory. Loop quantum gravity takes a different approach. It tries to apply quantum principles directly to space-time itself. In this view, space is not continuous but made of discrete chunks, tiny loops of gravitational field woven together like a fabric. Time emerges from the dynamics of this fabric. It ticks forward in discrete steps, Planck time by Planck time. Loop quantum gravity makes predictions that differ from general relativity at extremely small scales. But those scales are so small that we can't yet test them. Other approaches exist too: causal dynamical triangulation, asymptotically safe gravity. Emergent gravity theories that suggest space-time itself arises from something deeper. Quantum information, perhaps, or entanglement, or structures we haven't yet imagined. None of these approaches has yet succeeded. Quantum gravity remains unsolved, but whatever the solution turns out to be, it will almost certainly change our understanding of time, because time is central to both quantum mechanics and relativity, and the tension between them is most acute precisely when it comes to time. In quantum mechanics, time is a background parameter, a stage on which quantum events unfold. It's not quantized, it's not dynamical, it just flows smoothly and uniformly. In general relativity, time is dynamic, it stretches and compresses. It's affected by matter and energy. It's part of the thing we're describing, not a background for describing other things. Reconciling these two views of time is essential to solving quantum gravity. And the solution might reveal that time is even stranger than we currently believe. Perhaps time is discrete at the smallest scales. Perhaps it emerges from something timeless. Perhaps the flow of time is an illusion, a consequence of how quantum information is processed. We don't know yet. But finding out is one of the greatest adventures in science. Let's explore something that bridges physics and philosophy. Something that has puzzled thinkers for millennia and continues to challenge us today: the arrow of time. Why does time have a direction? Why do we remember the past but not the future? Why does entropy increase? Why do things fall apart but never spontaneously come together? The laws of physics at their most fundamental level are time-symmetric. Run the equations backward and they work just as well. A video of planets orbiting the Sun looks perfectly plausible whether you play it forward or backward. The same is true for colliding billiard balls, for bouncing atoms, for interacting particles. At the microscopic level, there's no preferred direction of time. The physics doesn't care. And yet, at the macroscopic level, time clearly has a direction. Ice cubes melt in warm water. They never spontaneously form. Eggs break when dropped. They never reassemble. People age. Buildings crumble. Stars burn out. Everything runs down. Everything decays. Everything moves from order to disorder. This is the second law of thermodynamics. Entropy always increases. The universe moves inexorably from low entropy states to high entropy states, from order to chaos. But why? If the fundamental laws are time-symmetric, where does this asymmetry come from? The answer, as far as we understand it, lies in the initial conditions of the universe, the Big Bang. 13.8 billion years ago, the universe began in a state of extraordinarily low entropy. Matter was distributed almost uniformly. Everything was hot and dense and smooth. This might sound chaotic, but it's actually a very special, very ordered state, gravitationally speaking. As the universe expanded and cooled, gravity pulled matter together. Stars formed, galaxies formed, planets formed, complexity emerged. All of this represents entropy increasing. The universe is running down, spreading out, moving toward equilibrium. And we are along for the ride. Our memories point toward the past because our brains are physical systems embedded in this entropic flow. We remember the direction of lower entropy. We anticipate the direction of higher entropy. The arrow of time is the arrow of entropy, and both point the same way because of how the universe began. This is sometimes called the past hypothesis, the idea that the universe started in a very special low entropy state. Without this assumption, the second law of thermodynamics doesn't work. You can't derive it from the time-symmetric fundamental laws alone. You need the boundary condition, the initial state, the Big Bang. But this raises a deeper question. Why did the universe begin in a low entropy state? Why those initial conditions and not others? This is one of the great unsolved mysteries of cosmology. Some physicists appeal to anthropic reasoning. If the universe hadn't started with low entropy, complexity could never have emerged. Stars wouldn't shine, life wouldn't evolve, minds wouldn't exist to ask the question. We observe low entropy initial conditions because we could only exist in a universe that had them. Others find this unsatisfying. They seek a dynamical explanation. Some process that drove the early universe to low entropy. Inflation, the rapid expansion of the very early universe, might play a role. But inflation itself requires special initial conditions. The mystery pushes back, deeper and deeper, until we hit the limits of current knowledge. Some physicists have proposed more radical solutions. Sean Carroll, among others, has suggested that our universe might be part of a larger multiverse, a system where new universes continually bud off from existing ones. In this view, there is no initial condition for the whole system. It's eternal, infinitely extended in both temporal directions. Our Big Bang is just a local event, a fluctuation in a larger timeless structure, and the arrow of time in our region reflects nothing more than the local increase of entropy since that fluctuation. This is speculative, highly speculative. We have no direct evidence for a multiverse, but it's the kind of speculation that serious physicists engage in when trying to make sense of deep puzzles. The arrow of time is one of those puzzles, and solving it may require rethinking everything we thought we knew about the beginning and end of the cosmos. Let's talk about the end, the far future, the ultimate fate of the universe. Because if we want to understand time, we need to understand where it's going, not just where it came from. Current observations suggest that the universe will expand forever. The expansion is accelerating, driven by something we call dark energy. We don't know what dark energy is. It makes up about 68% of the universe's total energy content, but its nature remains mysterious. All we know is that it's pushing galaxies apart, faster and faster, and it shows no signs of stopping. If this continues, the universe faces a cold, dark future. Over the next few billion years, the Milky Way will merge with the Andromeda Galaxy. The collision will be dramatic, but not catastrophic. Stars are so far apart that most will pass by each other without incident. A new, larger galaxy will form. Astronomers have already given it a name, Milkdromeda. But beyond our local group, other galaxies are receding, accelerating away from us. Eventually, they'll cross a threshold. They'll be moving away so fast that their light will never reach us again. They'll fade from view, red-shifting into invisibility. The observable universe will shrink. In the far future, our descendants, if any exist, will see only the stars of their local group. The rest of the cosmos will be dark, empty, gone. Then the stars will die, the smallest red dwarfs will burn for trillions of years, far longer than the current age of the universe, but eventually they too will exhaust their fuel. The last stars will flicker out. The universe will enter the degenerate era, a time of cooling stellar remnants, white dwarfs, neutron stars, black holes, slowly radiating away their remaining heat into the void. Even these remnants won't last forever. Over unimaginable timescales, protons may decay, matter itself may dissolve. The black holes will evaporate through Hawking radiation, a process that takes an almost inconceivable amount of time. A supermassive black hole might take 10 to the 100th power years to evaporate. That's a 1 followed by 100 zeros. Longer than any timescale we can comprehend. But eventually even the black holes will be gone, and the universe will enter its final state, the heat death. A vast, cold, empty expanse, uniform temperature, maximum entropy, no energy gradients, no complexity, no change, no time in any meaningful sense, because without change, without events, what does time even mean? This is the ultimate fate of the cosmos, not a bang but a whimper, not a dramatic ending but a slow fade into eternal stillness. The arrow of time will finally reach its destination, entropy will be maximized, and the universe will rest forever. Or will it? Some physicists have speculated about what might happen after heat death. Quantum fluctuations could produce random events even in a maximum entropy state. Over vast enough timescales, anything that can happen will happen. New Big Bangs might occur. New universes might bubble into existence. New arrows of time might emerge, pointing in new directions. Eternity is a long time, long enough for the improbable to become inevitable. These are speculations beyond speculations. We have no way to test them, no way to know if they're true, but they remind us that the story of time might not have a final chapter, that even heat death might not be the end, that the universe might be cyclical or eternal or stranger than we can imagine. Let's return to something more immediate, the human experience of time, because we've been talking about physics, equations, experiments, cosmic scales. But time isn't just an abstract concept, it's the medium of our lives, the substance of our experience, the thing we spend and waste and treasure and fear. Our perception of time is not the same as physical time. Psychological time is elastic, subjective, dependent on attention, emotion, and memory. When you're bored, time drags. When you're engaged, it flies. A week of vacation can feel like a month. A month of routine can feel like a day. Our brains construct our experience of time from memory and anticipation. And that construction is imperfect, biased, easily fooled. There's a famous phenomenon called the oddball effect. If you show people a series of identical images, then throw in one different image, the different one seems to last longer, even if it's displayed for exactly the same duration. Our brains pay more attention to novel stimuli. and attention dilates subjective time. The same thing happens with fear. In life-threatening situations, people often report that time slowed down, that events unfolded in slow motion. Studies have shown that this isn't because our perception actually speeds up. We're not processing more information per second. Rather, we're laying down more detailed memories. And when we recall the event, that richer memory makes it seem like it lasted longer. Time didn't actually slow down. It just feels that way in retrospect. This is humbling. It means our sense of time passing is not a direct readout of reality. It's a construct, an interpretation, a story our brains tell us based on fragmentary information. Physical time may be relative, as Einstein showed, but psychological time is even more relative, even more personal, even more uncertain. And yet, this constructed sense of time is what makes us human. Our ability to remember the past and anticipate the future defines us. It lets us plan, learn, regret, hope, dream. Animals with shorter time horizons live differently than we do. They're more bound to the present moment, more reactive, less reflective. Our extended temporal consciousness is a gift and a burden. It lets us build civilizations, but it also lets us worry about death. Every human culture has grappled with the passage of time. We've invented rituals to mark its milestones, birthdays, anniversaries, New Year's. We've created art to capture fleeting moments, photographs, songs, poems. We've built monuments to defy decay, pyramids, cathedrals, data centers. All of these are attempts to push back against time's flow, to leave something that lasts, to matter beyond our brief moment in the cosmos. And we've invented stories about transcending time altogether. Religious traditions speak of eternity, of souls that exist outside time, of heavens where death and decay are no more. These stories comfort us. They help us face the inevitable. They give meaning to lives that are, by cosmic standards, unimaginably brief. Physics neither confirms nor denies these stories. It tells us that time is stranger than we thought, that it's relative, personal, entangled with space and gravity, that it might be an illusion emerging from something deeper. But it doesn't tell us what happens to consciousness when the brain dies. It doesn't tell us whether subjective experience requires time or can somehow exist without it. These questions remain open, perhaps forever. What physics does tell us is that our experience of time is precious, that it's not universal, that photons and black holes and the far future heat death of the cosmos all exist in temporal states radically different from our own. We, with our memories and hopes and fleeting present moments, are rare, special, a tiny pocket of temporal complexity in a universe that is mostly timeless, or moving toward timelessness. But have you ever wondered what would really happen if humans tried to travel at the speed of light? In this video, discover the terrifying physics that make light-speed travel not just impossible, but deadly. See you there.